Okay, so let's try to wrap up on this angular momentum business here. We're going to see the laws of mechanics for a rigid body today. And then next time we'll do a problem that will be a pretty long one. Maybe we'll take a couple times, but can show how we apply all these concepts. So this is where we were last time. Let's summarize what we've seen. We said that the angular momentum in an inertial reference frame with respect to the center of mass can be expressed as the inertial tensor with respect to the center of mass of the body R, which is a rigid body, dotted with the angular velocity of the rigid body with respect to the inertial reference frame. We have proven that I, when we write it in a body fixed coordinate system, center, of course, at the center of mass, E1, E2, E3, if we do this, well, then we can write it as a pretty long expression, I11 bar E1 circle cross E1. Let me write the whole thing just once. And this is E1 circle cross E2 plus I13 bar E1 circle cross E3. And on purpose, I will put it in this order here. I21 bar E2 circle cross E1. I think you get where I'm going with this. But I want to write the whole thing. So this is 2, 3 bar E2 circle cross E3 plus last row is the last row is I3 1 bar E3 circle cross E1 plus I3 2 bar E3 circle cross E2, and finally I33 bar E3 circle cross E3. So this would be the inertial tensor expressed in a body fixed coordinate system, which has a center at the center of mass. And we said all these i's here are, the beauty of these is that these are constants. So you have them on tables. It's really a lookup table. So we're going to write them here. But they are computed for different shapes of different bodies for you, for cylinders, cubes, etc. You can find them on books. So you don't really need to care about these. They are given to you. So this is integral of rho 1 squared plus rho 3 squared dm. But you need to know what they are, of course. I33 integral over r rho 1 squared plus rho 2 squared in dm. And then, so this is where the moments of inertia, and then we have the products of inertia, I bar 1, 2, which is equal to I bar 2, 1, which is minus integral over the body of rho 1, rho 2 dm. Then we have I2, 3, for example, which is equal to I2, 3, 2, bar minus integral over the body rho 3, rho 2 dm. And finally, this is the only one I'm missing, 1, 3, which is equal to 3, 1. Always the bar on top because this is with respect to the center of mass, rho 1, rho 3 dm. And these are what we called products of inertia. So again, these are given to you in books. And that we'll see in an example that there is also particular coordinate systems where the products of inertia are 0. So what you actually get in books are these, are the I11, 2, 2, and 3, 3. They're constants. So all these quantities, these constants here, represent how the mass is distributed on the rigid body. The shape, so here what you see coming into place is the shape and the mass distribution on the rigid body. So they are computed once and for all. Why is this beautiful? Because if you put it in the form of a matrix, which is what you have probably seen all the time, you can compute the components of h bar in this coordinate system, h1, 2, 3, as the product of these, and this is again, it's an abuse of terminology, inertia matrix. This is a representation of a tensor in a particular basis. there is an inertia tensor. There is no inertia matrix. This is just a projection of the tensor on a particular basis. I2 2 bar, I2 3 bar, and then here I have 3 1 bar, 3 2 bar, 3 3 bar, just multiplying your angular velocity vector, right? Expressed or projected in a particular coordinate system, which is that body fixed coordinate system. This is what you've probably seen all the time. But again, this is once I've locked the coordinate system, I've decided to use that one. But this is the general expression. So this is what we have seen last time. One other very important result that we demonstrated is the following. Don't need this anymore. It is this result that allows me to go to any point. So Q is any point in E3, 3D Euclidean space. We have this result that AQ, H with respect to Q, in N minus H bar in N is RQ minus R bar cross with M V of Q in N minus V of the center of mass, velocity of the center of mass in N. So you can once and for all get these moments of inertia and products of inertia and assemble these tensor here, and that gives you H bar. Once you apply it, you multiply with the angular velocity. And then once you have H bar, which it's easy to get because those are constants, you can always go to another point knowing its position, its velocity, and of course the position and velocity of the center of mass. So I'm going to show you how we derive from this the parallel axis theorem, which you shouldn't really use because it will force you to go through the calculation every time that we've done to obtain these constants here. And what's the point? You do it once with respect to the center of mass, and then you use this formula to go to another point. You don't need the transport theorem, as I will show you in a second. So these are very important results. This is something we can compute. This is given in tables. Now, do we all understand why this is true? Why I can write H in the coordinate system E1, E2, E3 that way? So remember, we have the inertia tensor will be composed by elements like, for example, I11 bar E1 circle cross with E1 and plus other terms, right? These, in that formula, is dotted with omega 1 E1 plus omega 2 E2 plus omega 3 E3, right? So you obtain that form if you put it in a matrix when you start doing all these products. If you start doing E1 circle cross with E1 dotted with E1 itself, what do you get? Remember the definition of tensor product? What does this give me? This gives me E1, right? And you apply the same with all the other products. You do it with the second one, and you keep going, and you will get that form in general. So anyways, that's where this is coming from. It's just a projection of these vector expression where there is a tensor and vectors. Now, parallel axis theorem. Something we can prove here is really nothing special, but there is no point in doing it ever because we have that. This is really the one that you may want to remember / highlight in your book. This one and this one. So do you remember, if you've taken dynamics or studied these somewhere else, what does it allow you to do, this parallel axis theorem? I have my rigid body R, right? I said that I pick the center of mass and a body fixed coordinate system. So this is the center of mass. What do you do when you apply the parallel axis theorem? Remember? That md squared, something like that. Well, we do it here in 3D. We don't do any simplified cases here. The parallel axis theorem allows you to now compute the angular momentum with respect to another point working on the inertia tensor. So basically to write the inertia tensor with respect to another body fixed point, which can be called B, for example. And it's called parallel axis because I'm not going to change the orientation of the coordinate system. It's still E1, E2, E3. It's just another point. So that's why it's called parallel axis. I just translate this and shift it in B. Well, let's see what happens. How do we get the formula that you have seen in a simplified way probably somewhere else? I apply that. HB in N is equal to H bar in N plus RB minus R bar cross M VB N minus V bar N. Okay? Now, this vector here is this guy, right? Sorry, my vector is a little curved. It's not supposed to be, but let's call that, I think your book calls it pi. Now, today is going to be a lot of vector calculations. I'm sorry, but I need to go through that. What is true about this thing here? So this is, I called it pi. What is true about this velocity difference here? There are 2 points that are fixed with respect to the rigid body, right? The center of mass and another point that I pick, which I said is fixed with respect to the rigid body. They are both fixed in R. Doesn't matter if the center of mass is actually on the body or outside. If this is a donut, still the center of the donut will be fixed with respect to the donut itself. So what is true about this? One of the properties we derived for rigid bodies. We derived 2 things at the beginning when we started kinematics of rigid bodies. Remember? When you pick 2 generic points on a rigid body, there is a way to relate their relative velocity and accelerations. Very first lecture when we started kinematics of rigid bodies. If A and B are 2 points on a rigid body, what is this? Remember this? Remember we also derived something with the accelerations? And again, I'm using N here, but you can have another reference frame. And there was something else here with alpha and omega. So we derived these 2 expressions here. So what I'm getting at is that my A in this case is B, and my point B is actually the center of mass. So I can write this like omega Rn cross with pi, right? Okay. Nothing that we do in this class can be forgotten because we've done it and you've done a test. It's all accumulating here. You can't forget anything. It's all part of the same picture. So, okay, so this is going to be H bar, which let me write it like that. It's I, the tensor of inertia of the body with respect to the center of mass, dotted with omega Rn, plus I get this M pi cross with omega Rn cross with pi. Agree? Do you remember when we started talking about the inertia tensor? I copied from my notes the triple double cross product expression because I have no idea how to memorize that. And we ended up writing the tensor. So if you go back to your notes, you can prove to yourself that this is equivalent to writing pi dotted with pi unit inertia tensor minus, I'm doing it with rho here, pi circle cross pi. What I called rho before, this is just pi now. Do you remember this? A couple of lectures ago, probably, before the break, probably. And so, if I go here now, and I don't want to erase this formula here, that is telling me that H, B in N is equal to I R dotted with omega Rn plus that thing there that I'm writing as plus m. Oh, forgot one thing. Let me rewrite it here. Give me a little more space. It's pi dotted with pi u minus the tensor product between pi itself dotted with omega Rn. That's exactly what this is. Again, go back to your notes. It's pretty simple. Just replace pi with rho, and that's what happened at some point. And so plus m times all that. Minus pi, circle cross pi, dotted with omega Rn. Well, what is this? What is this ugliness here? I'm not asking you a specific question, just in general, what it is. Is this, oh, this is a vector, by the way. Is this a scalar? Is this, what is this? A vector? That's a tensor, right? Oh, yeah. It's a tensor. So I can rewrite this whole thing the following way. Just collect this angular velocity. All right. It's multiplying both of them. Okay, here is your new tensor, which is now the tensor of the body with respect to B. That's what I've done. That's what you do with your transport theorem. You take your inertial tensor and you move it, compute it with respect to a new point, keeping the axis of the coordinate system fixed to the body where they are. You just move them to another point, which is not the center of mass. And so as you can imagine, if for some reason when you're solving a problem, it's more convenient for you to go to a point which is not the center of mass, where your tables will tell you how to assemble this thing. Again, they are on the, the back cover of a book probably. So you know how to build these, but in some cases it may be easier to go to another point. It's not always the case that using the center of mass is the best solution. And so what do? You redo it again, because you have to tell me what this is. You have to recompute this thing again. I've just done it with wasting I don't know how many boards with all the integrals and telling you, yeah, they are on a book. Are you going to do it again for every single point that you need to choose to solve the problem? That would be craziness. So you don't do this. I strongly advise against this thing. Even though you do it in a plane, in a planar problem, and that becomes easy because in a planar case, this simplifies to that md squared that you may remember. Forget about that. Use this. This is telling you how to go to another point. Replace Q with B. It's just another point. And this still holds, because Q here is a generic point, so it's perfectly fine to pick a body fixed point. All you have to do here is a cross product between two vectors and two velocities. It's much easier than doing another tensor again. So from now on, the only thing you need to care about is the inertial tensor with respect to the center of mass, which is in your tables, in your book. And then if you need to move to other points, you have the tools to do it. So you deal with tensors just once and for all. Okay? This is my comment about the transport. Keep calling it transport. You're transporting the point. The parallel axis theorem. Now what do we do with all this stuff? Can I start erasing here? Maybe I'll go on the other side. We want to use it, right? We talked about angular momentum enough now, and we want to start solving problems. Kinetics here. How do we do it? Well, we have to think about the following. We have a rigid body, and a rigid body has how many degrees of freedom, how many variables will you need in general in 3D Euclidean space to tell me where it is and how it's oriented? 6, right? 6 degrees of freedom. And we say that 3 go for translation, which is basically looking at the center of mass. And 3 will go for rotation, which is, well, we talked about angular momentum, so we will probably have something to do with some angular momentum with respect to a certain point, right? Or angular velocity. Think about what you have here. You really have a tensor applied to the angular velocity, so you're just doing an operation of angular velocity, on angular velocity. So this is what we have. Now I want to do kinetics. I want to think about what is changing the motion of this object in translation and rotation. So far we've seen forces, right, for particles and systems of particles. Well, forces can affect translation, that's for sure. But they can also affect rotation. You can have a force applied to a rigid body, and that force causes a change in orientation, right? This is my rigid body here, and I just apply a force on this side, it will rotate. So that's fine. We can definitely have forces on a rigid body. But what if you want to think about cases where the rigid body is only rotating, which is possible? So we introduce the concept of pure torque. Which is something we represent on the rigid body like this. We call it tau. And we say that this is my definition of pure torque. A pure torque can be thought of as a couple of forces that have zero net sum. So I can replace tau with this. F applied to some point, the same exact force but the opposite, minus F. And so this is, say this is point A, this is point B, the midpoint is called P. And I'll show you that if we define the torque, the pure torque, this way, its effect is completely independent on the point from which you compute its moment. So if I pick P here, or I pick a point Q up here, whose position with respect to P is called R, I will still get the same thing. So I need something that has zero net force, so it's not going to affect translation of the rigid body, but affects rotation, and it doesn't really have anything to do with any specific point, because forces will be, of course, applied to specific points on the body, but not the pure torque. So, well, let's do it. What is the moment with respect to P due to those two forces? It's rho crossed with F. I forgot to call these vectors. I want to call this vector from P to B, I want to call it rho, and this is, of course, minus rho. Can you all see it? So the vector P to point B is rho, and what is it? P to A is minus rho. So I'm computing the moment of those two forces with respect to P, minus rho cross with minus F, and this, of course, is going to give me 2 rho cross with F. If I do the same with respect to another point, generic point Q, this is going to give me R plus rho cross with F plus R minus rho cross with minus F, and you can easily show to yourself that this is also going to give you 2 rho cross with F. So we start imagining this action that you can have on a rigid body where it's in fact two forces, but they're equal and opposite, and so it doesn't really matter where you apply them, you will get the same effect on the rotation on the body. Because as you can see, I keep changing the point here, I will still get the same final tau. This is my tau. So pure torque is independent from points. Okay? Make sense? It's when you grab an object and you twist it. It doesn't matter where you do it. That's my pure torque. So these are the actions that I model as things that can change the status of motion of my rigid body. Forces, we've seen them, pure torque. And so my picture for a generic rigid body will look like this. I will have R. I will have, in general, probably a pure torque acting on it, and then a bunch of forces, F1, F2, F3, Fn, acting on the body. And so the general action will be, in terms of forces, will be a summation of all the forces. This is what I call the resultant of all forces acting on the body, F. And then I have the moment with respect to a generic point q. Remember, q for now is a generic point. It doesn't have to be on the body, it doesn't have to be inertially fixed, it doesn't have to satisfy any requirement, it's just a point. So this will be given by r, okay, summation over summation I that goes from 1 to n of ri minus rq. Of course, ri are the positions of the points where the forces are applied, cross with fi plus tau. So here I'm just writing, formalizing what those two actions are. These are all the forces acting on my rigid body. This is the total moment due to forces plus the pure torque that act on my body. So that's what I have. That's all I'm going to assume it's happening to my rigid body. And now I want to relate finally the kinematics that we've seen, which is basically acceleration of center of mass and the angular momentum, to these two things here. And as same as we've done in the case of a particle, and then we extend it to a systems of particles, we're going to introduce laws. That means that I don't need to derive them. I don't need to convince you they are true. If you don't believe them, you take a rigid body yourself, and you run thousands of experiments until you prove that they're wrong, but good luck with that. Because so far, no one has proved them wrong. So these are Euler's laws for the mechanics of a rigid body. Again, they're laws. I'm not going to derive them. The first tells me that F, the summation of all forces acting on the body, is going to equal m acceleration of the center of mass of the body in the inertial reference frame, in any inertial reference frame. No surprise with that, right? We've seen it before for a system of particles, but in that case, I derived this. In this case, I'm telling you, I'm not deriving this, I'm just giving it to you. Again, if you don't believe this, you grab a rigid body, you start applying forces to it, measure the acceleration of center of mass, you know the mass, and try to see if it works. It's a law. The second one tells me that MO is equal to d dt in n of HO in n, where O is a point which is inertially fixed. Okay? These are the two things that you need to solve problems that have to do with rigid bodies. What are you going to do in practice? The same that we have done so far. You look at a rigid body, you first solve for the kinematics, and kinematics in this case, what is going to be kinematics here? What do you think is kinematics for a rigid body? What do you need to compute? You need two things, right? In this case, we have translation and rotation. You need the acceleration of the center of mass in an inertial reference frame. And in this case, the way I gave you the law, you need the angular momentum with respect to an inertially fixed point in the inertial reference frame. Right? The laws tell me that, so that's what I need to do. So you first solve for these two, then you do your free body diagram to compute F and set this equation, and then you have to compute the moment of all forces plus the pure torque to give me the moment with respect to O. Now this is relatively, I don't want to say easy, but this is already done. The first one, we've done it several times. You need to focus on a point on the rigid body, compute it, find its acceleration, and then all the forces and set that equation. So the second one is the one that needs a little bit of work, because no one, except in some problems where it may be easy to do, no one wants to do things with respect to an inertially fixed point, unless it's a special case and it's obvious that it's advantageous. But I do spacecraft work, so if my Earth here is my inertial reference frame, which is an abuse, but we do that all the time, and we say that this is my inertially fixed point, and I create some coordinate system fixed with the Earth, and I look at a satellite going around, and this satellite, say that it's a CubeSat, just for fun, so it's a cube, and it's a rigid body, and I want to study how its orientation is changing. Do you really want to compute h of this thing with respect to this point down here, which is 7,000 kilometers away? It's going to be a nightmare. So for some cases, it's really not a good idea to use an inertially fixed point. But unfortunately, Euler tells me that that's what you need to do, at least for now. Well, let's change that a little bit. So I'm going to use the second law, but I'm going to try to see if I can do something with a different point. So I don't think we need this here. Let's do the following. Let's introduce the usual Q generic point, right? Q is a generic point. Generic means, again, not on the body, not fixed in any reference frame. It's just a point. And I need to write the following things. I will need them. So the moment with respect to this O inertially fixed point is, by definition, is the summation of all these Ri's minus Ro cross with Fi plus tau. If I do the same with respect to Q now, it's going to be a very similar expression. The only difference is that instead of Ro, I have Rq here, cross with Fi plus tau. Subtract the two, and we'll write it on one side because we need it. Mo minus Mq. Start thinking about this. Similar terms will go away. All these Ri's will go away. So you will have summation of Ri over I Rq minus Ro cross with Fi. The torques go away. It's the same torque, right? Again, the torque, I just defined it as something that does not have anything to do with the point. So the same tau that I have here appears here. It doesn't matter if I'm doing M with respect to O or Q. So it goes away. Do we agree with this step here? When I subtract the two, all these Ri's will go away. Agree? So this is what I'm left with. Now, Rq minus Ro is not dependent on the summation, right? Can take it out. So this is Rq minus Ro cross with the summation of all forces, and I said that this is F. So let me write it here on the side, the final result, because I'm going to use it very soon. So if I just have two generic points, in this case one happens to be inertially fixed, but really there can be any points. Mo minus Mq is going to be equal to Rq minus Ro cross with F. And that stays there. Now, so let me just box it so I don't erase it, hopefully. I'm going to do the same thing with H. H with respect to O in N. I know that I can always go back to my center of mass coordinate system plus, what is this? Ro minus R bar cross with M V O in N minus V bar in N. We demonstrated this. The same will be valid for Q. It's going to be equal to H bar N plus Rq minus R bar cross with M VO, VQN minus V bar N. Subtract the two, you get that HO N is equal to HQ, and I'm just bringing these on the other side. These two will go away, and then I have all this stuff here. So are you okay if I start doing the cross products without rewriting that I have this term minus this term? Is that okay? So actually, I may not want to do them now. Actually, let me forget what I said. I'm just going to rewrite them because there's one more thing that I need to do. MVO N minus V bar N, and then I have minus. These are the cross product here. Sorry, today is a lot of vectors, but this stuff is important. Okay, so this is what I have. Now, remember that my second law tells me that at some point I need to take the derivatives here. So if I take the derivative of that, d dt, of course in the inertial reference frame, of H, O, n. Remember that this is, first of all, it's MO, right? Which is also equal, by that calculation, MQ to MQ plus RQ minus RO cross with F, and just we'll leave it there. But let's start taking derivatives there. So this is going to give me, on the right-hand side, from the right-hand side, d dt in n of h with respect to q in n. And that's the first one. Now, let's save some time here. And notice that when I start doing the derivatives of these cross products, I use the product rule. So the derivative of RO minus R bar with respect to the inertial reference frame is going to be VO in n minus V bar in n. Agree? So these will go to 0, the first one. So what I'm left with is simply RO minus R bar cross with M. Let me save even more time here. Now I'm doing the derivative of this term, VON minus V bar n. What is the acceleration of O in the inertial reference frame? 0. It's an inertially fixed point. So I'm left with minus A bar n. And then the second one, same type of reasoning. The first derivative, it's on RQ minus R bar, which is going to give me VQ in n minus V bar in n. So cross with itself is 0. I am left with RQ minus R bar cross with, now the accelerations unfortunately remain there. I have AQ in n minus A bar in n. Now I'm doing the cross products. d dt in n h. I know where I'm going with this, so that's why I am just going like this. So okay, let's do the first cross product. RO, so that's a minus. RO cross with M A bar in n. That's the first one. Then I have the second one, minus minus is plus, plus R bar cross with M A bar in n, and that takes care of that. Second one, start with RQ. RQ cross with AQ with a minus. Correct me if you see any sign problems here, please. So then I have to go back. Okay, then RQ with this, it's minus minus is plus, plus RQ cross with M A bar n. And unfortunately I have to go down here. Now I'm looking at R bar crossing with these accelerations. Minus minus plus, I have R bar, right, cross with M A of Q in n, minus minus and minus, so that's another minus, minus R bar cross with M acceleration of the center of mass in the inertial reference frame. Is there anything that goes away? No? Yes? Maybe? These two go away. Right? So if I continue here, still have this d dt in n of h q n. And then let's collect the accelerations now. So A bar appears here. Where is it? And down there, right? And here. So I see an RQ plus, RQ minus RO cross with MA of the center of mass. And that's that. And then the other one shows me an R bar minus RQ cross with MAQ in N. Forgot anything? I don't think so. Okay, why did I go through the pain of doing all this? I said that this is equal, remember, this is just another way of writing the rate of change of the angular momentum with respect to inertial reference frame of HON, right? So this is also equal to that, MQ plus RQ minus R0, or I'm sorry, RO cross with F. So this is equal to this, right? Okay? What can I do now? There's something here that I should notice. Something goes away, right? First law tells me that this is what? This is total force. The resultant of all forces acting on the body. So this is F, and this is the same term. And it should go away, and it does go away. Oops. Okay, let me write it up here. So my basically final result is now this is stuff that will allow me to do some examples that have to do with spacecraft at some point. So things will become a little more fun. So I'm left with MQ plus RQ minus R bar cross with MAQN. I'm just bringing this term on the other side, right? And that's going to be equal to d dt in n of HQN. That's another way to write the second law. This is still the second law. I haven't changed anything. I just moved things to another point. I just moved everything to a generic point. Remember, Q is any point. So this is what you do if you don't want to do with respect to an inertially fixed point. Now, what do you notice here? Do you notice anything? Do things become familiar if something happens there? Q is any point. I'm free to pick that point.
So if you pick the center of that.
Right. What if RQ is R bar? See what happens there. This goes to 0. So I get d dt in n of HQN equal to MQ. But now Q is the center of mass, so basically this becomes M bar, and this is H bar. It looks exactly the same as the second law. So you can basically write the same kind of expression with respect to the center of mass. It doesn't have to be an inertially fixed point. The center of mass is definitely, in general, not an inertially fixed point. But that's valid. So you do have these tools. You have the two laws. You have F equal M A bar in N. And you have these or these that you can use to solve problems with rigid bodies. That's all we need to have. Again, I know there is a temptation. We've done this with the angular momentum for a particle. I know that it's tempting to bring things to the center of mass because these, as it is on the board, looks better than this one here. But it's not always the case. This is just nicer because it looks like the second law of Euler, but you may pick a point where things don't simplify that much, and it's better to use this one. So the line of thinking, I will start seeing a problem. Maybe I'll just draw it and we'll do it next time. But the line of thinking is, these are your ingredients for solving kinetics problems with rigid bodies. The angular momentum expressions, second law in different forms, these two forms, that's what you have, and the first one. You may be able to solve problems, as we'll see next time, by just using the second law of Euler if you pick the right point. If you pick a point where your unknown forces, for example, may just not contribute to M, so either M bar or MQ, then you don't have unknown forces. So this may give you an equation of motion just right away. If you pick the wrong point and you still have unknown forces like reactions, static friction, well, you may not get, from using the second law, an equation of motion. You still have some unknowns, so you have to go back and apply the first law of Euler to actually get rid of the unknowns. And I think we've seen some examples so far where that happens, right? If you pick the wrong point. So again, don't fall for the temptation to use this just because it's, wow, it's cool, there is less stuff. because computing this may be actually pretty easy, and your MQ may have all known forces in it, while your M bar has a lot of forces that you don't know. So you're not really saving time by doing that. And I'm just going to draw it here, and then we'll finish it. We'll actually start doing it next time. Standard problem. This is standard stuff. You want to do these basic problems because they show how to use the theory. And it may seem simple at first sight, but there is a lot of stuff to do here. So an inclined plane here, angle beta. This is also inertial. And we have a cylinder that is rolling down. Okay? Now this is a rigid body though. And I think I'll call this point Q, the point of contact. There is roll without slip. And let's call the center O. And the radius R. And there is gravity. Right? Okay. Thinking if I forgot anything, I don't think so. And I want the equations of motion, of course, of this rigid body. Now this is a rigid body. Let's call this disk D. I want the equations of motion. Well, what I will usually do in problems, I would also give you some angle here for the rotation of this, right? I'll give you some parameter, theta. So I invite you to start approaching this problem before we start doing it next time. The things that I want to highlight is we'll do at different points. We'll start this. So this is, of course, the center of mass, right? So if the cylinder is uniform. When you do your free body diagram, I'm just going ahead of myself, but just to make you think a little bit. You will have the force of gravity, mg, applied to the center of mass, and then there is contact here, right? So you have some reaction force that goes like this, which you don't know. There is also something else, right? What do you think? What makes this thing roll without slip? Friction. What kind of friction? Any of the two we've seen? It's static friction. There is no VREL, right? If I'm telling you there is roll without slip, it means that the velocity of point Q seen by an observer fixed in n as part of n is the incline, it's the same thing. You can call it ground. We can call whatever you want. It's also equal to the velocity of Q as part of the disk seen by n. But this is 0. So this is 0. There is no VREL. But yet there is friction. So it's none. The friction forces models that we've seen, two of them, Coulomb and viscous frictions, those are dynamic frictions. For those I can write an expression. They are not unknown. Remember, we compute VREL and I just put together a formula. So you know them. Now this static friction, it is an unknown. It's exactly like this n. I have no idea. I know the direction, but the line of action, but I have no idea how to write a formula for it. So it will be an unknown. And so you can imagine how when you start solving your problem with respect to the center of mass, or with respect to this point, some things go away depending on the point in computing the moment. If you pick this, the gravity will go away. This will probably go away, but this doesn't. If you pick this point, these two guys go away. They are the two unknowns. So in this case, point Q, again, we'll go into the details of this, may actually be better or maybe a smarter choice. So you actually use this form of second law rather than that one. And with applying just that, you may get an equation of motion. Instead, if you pick the center of mass, it may not be sufficient, and you still have to do the balance of forces and write yet another equation to get rid of the unknowns. So there is no right or wrong way of doing it. It's just think ahead before you pick the point and before you do calculations, because it may save you time. But again, we'll start doing this a little better next time. Thanks.